In this video, we're going to look at resonance structures. So let's start with NO3 1 minus, or the nitrate ion. So take a second and see if you can draw a dot structure for that. Go ahead and pause the video while you do that. Okay, so hopefully you took some time to see if you could put that together. We want the atom that can form the most number of bonds in the center. That's the nitrogen. Oxygens are going to go around. We're going to need at least one double bond to account for the total number of electrons. It is an ion, so we'll put it in brackets, put that 1 minus charge on the outside. So the question at this point is, which oxygen do you put the double bond on, and does it matter? And it turns out it does. Because they are different oxygens, and what we find with this ion is that electrons can redistribute themselves, and you can have a situation where that double bond will actually move and will form between that number one oxygen. And then again, we can have another situation where again the electrons redistribute, and we end up with a third possible structure. These structures are known as resonance structures, and there's a couple of different ways to think about it. We can think about it in terms of, again, those electrons shifting positions, the double bond shifting position. And so this ion is rapidly moving back and forth between all of these structures. So that's NO3. Let's take a second and look at what is actually going on here and what evidence there is to suggest that this does in fact take place. So we'll take a little bit of a deviation and go with it NO2 1 minus, that's the nitrite ion, and we'll look at what's called bond length. So bond length can be measured to some degree in the same way that we would measure atomic radius. We can use crystallography to shoot some x-rays at these things. We can figure out where the nuclei are. And so if you have nitrogen-oxygen bonds, generally it's the case that in order for an electron or two atoms to share two pairs of electrons, they're going to have to be a little bit closer. So single bonds are typically longer than double bonds, which are themselves longer than triple bonds. And so what you would expect to find if you were to run a crystallography reading off of this particular structure is a short bond and a long bond. So if you look at the table, it's up at the top here, we have the bond length in picometers of a nitrogen-oxygen single bond at 136. We have the nitrogen-oxygen double bond at 115. So again, you would expect to see one long bond and one short bond, but instead, what you see are two equal length bonds at 125. In a sense, it's as though each of these bonds is rolling at about 1.5. And so what we typically, how we typically describe the structure of this NO2 1 minus ion is as a resonance hybrid between the two structures, where the double bond on the left and the double bonds on the right, that it's actually two equally length bonds. Okay, so let's see if you can sort this out. So here is another structure for you to sort out, CNO1 minus ion. See if you can draw all of the resonance structures for that ion. You should go ahead and pause the video. You should give it a try, and then we'll post the answers here in just a second. Okay, so hopefully you gave it a try there. Again, the atom that can form the most number of bonds we typically put in the center, that would be the carbon. And so here are the possible structures. We can have a triple bond on the oxygen. We can have a double bond on each. We can have a triple bond on the nitrogen. So if you think about what's going on here, there are, 6 different types of bonds listed there in terms of carbon, nitrogen, single, double, and triple, carbon, oxygen, single, double, and triple. And yet again, the structure that you're likely to see for this thing is two equally length bonds that are some hybrid of all 6 of those options. And so those would be the resonance structures for CNO minus.